Hello everyone, welcome to the discussion of the acid-base imbalance. And in this topic I'm gonna discuss what are the basics of the acid-base imbalance are, because this thing gave me a hard time when I was reading this thing, and that's why I thought about it that okay, let's make a video at least uh, for the people like me who have hard time in understanding this thing. So that's why I'm making this video. You may not find it 100% accurate because I haven't gone through many textbooks. I just went through the first aid for USMLE Step 1, what I'm a tutor of USMLE Step 1, and also I went through some notes like from the question banks and all over the not all over, like I searched many things in the internet. So uh, that's just for a you can say a preliminary idea of acid-base imbalance. Okay, so let's start, and here you can see that what is the normal blood pH. First thing, normal blood pH is it differs, but this is a range. You can take it as accurate, like from 7.35 to 7.45. And I hope you know what is the pH is. pH means or it describes in a scale how much hydrogen ion we have in our body. The more the hydrogen ion in our body, the less the pH. And also you can say the more acidic um, our body or our blood, the less the pH. So 7.35 and 7 up to 7.45, this is the normal range of pH. And what is the normal blood bicarbonate level? You may ask me that why I am talking about bicarbonate, because when we go and discuss in these different diseases of the acid-base imbalance, you will see that this bicarbonate concentration and the partial pressure of carbon dioxide, this thing comes very frequently, and we kind of discuss over them. So that's why the normal bicarbonate level, I just wrote 24 because I couldn't find a good range for it, but it may be you can say 24 to 27, or sometimes I found 18 to 25, whatever. So this thing is, you can take it as, for this discussion, 24 milliequivalent per liter. Normal partial pressure of carbon dioxide, or you can say the plasma carbon dioxide, that dissolved carbon dioxide in our plasma, is it's 38 to 45 millimeter of mercury, but again the ranges change. Now, what is acidemia and what is alkalemia, or you can say what is acidosis or alkalosis? Simply that acidemia means there is more acidity in the blood, right? Emia, you know that we are very familiar with this subterm emia because we use anemia, right? Anemia means what? There's less blood. Emia means blood, and acidemia means acid in blood. So acidemia means there is acid in the blood, and you can guess that the pH will go down of our range, right? Because when the pH goes down, it means the H plus goes up, and when the H plus goes up, we say it as acidosis. Alkalemia, the opposite. That means the pH is higher, that means H plus is lower. Okay, so acidosis, it can be of different origin, and what we discussed, that acidosis can be of metabolic origin and it can be of respiratory origin. And that's why, remember, I told you that we're going to describe this bicarbonate and carbon dioxide more often. Like this bicarbonate, the change of bicarbonate that leads to acidosis, we call it metabolic acidosis. And the change of carbon dioxide that leads to acidosis, we call it respiratory acidosis. You can guess it, right? Because bicarbonate is a chemical, and maybe you are guessing now, okay, so bicarbonate is produced in our body and it is handled by the kidney and different places, right? So if there's problem with that metabolism of bicarbonate, it can lead to acidosis or acid production. And the respiratory means always it comes with carbon dioxide. That means we breathe out carbon dioxide, the simple thing, right? So when there is change in carbon dioxide and when there is change in bicarbonate level, and this change gives rise to this metabolic change in acid-base balance. There will be acidosis or alkalosis. Depends. We're going to describe. But simply, you see that acidosis can be metabolic and respiratory, alkalosis can be metabolic and respiratory. By the way, in advanced discussion, you will see that there may be some mixed type of acidosis and alkalosis, or there can be two mixed acidosis, two mixed alkalosis, or vice versa. Acidosis, alkalosis, alkalosis, acidosis. So there may be mixed type of diseases that can also happen. Now, to make our life easier, Mr. Henderson and Mr. Hasselbeck, they made this equation. I'm not sure, you may be cursing me right now, because this equation, whenever you say it, it makes your life harder than make your life easier. I'm just kidding. So Mr. Henderson and Mr. Hasselbeck together, I'm not sure if they're the same guy, maybe two different guys. They produced this pH calculating equation of our blood, and that is 6.1 plus in the log scale. Don't ask me what is log scale. I'm a math student. I'm not a math student, and that's why I don't know it. The log scale bicarbonate divided by 0.03 times partial pressure of carbon dioxide. So easy, right? Okay, don't curse me. So let's make it simpler. Let's make it simpler. Like this thing, this 6.1 or this log or this 0.3, just forget it. And if you write it like this, that pH equals the bicarbonate level divided by the partial pressure of carbon dioxide, then this thing becomes slightly easier, right? How? Because if I say, okay, if you increase the pH and if you don't change the PCO2, what will happen? This value will go higher, right? And you can say, okay, so if I increase the bicarbonate and no change in PCO2, the pH goes higher, and if the pH goes higher, we call it alkalosis, right? So as there is change with the HCO3, as I discussed earlier, that HCO3 is a metabolic thing. So when the HCO3 goes higher, you can say it a metabolic alkalosis. Or in the other way, you can say if the PCO2 goes down and there is no change in the bicarbonate, and that thing also leads to increase in pH, right? And that thing, what do you say? It's an respiratory dependent change in your respiration dependent change in your pH, or you can say it's a alkalosis that is due to change in my PCO2. Okay, so you can call it respiratory alkalosis, right? And you can play with it, right? Like you can say, okay, so if I, instead of increasing the bicarbonate, if I decrease it, what will happen? The numerator is decreasing, right? The numerator is the top part of the equation. A by B, A is the numerator and B is the denominator. Okay, by the way, I'm not a math student, I'm a med student. Okay, so this thing, that when the bicarbonate goes down and you see the pH goes down, and pH goes down means there is acidosis. So you can say that bicarbonate goes down and pH goes down, and this bicarbonate, as we are discussing it as a metabolic thing, so you can say the bicarbonate goes down, pH goes down, it is a metabolic acidosis. Or you can say it the other way, like if you increase the PCO2, if you increase the PCO2 and pH, this equation, because you are increasing the denominator, and this equation will give you a leisure value, or simply the pH will go down, what will happen? That you will say, okay, so this is an acidosis due to change in the PCO2, so you can say it as respiratory acidosis, right? So this is a simpler form of Anderson-Hasselbalch equation, not too bad, right? So this pH change, you can get it into this table. We love table, right? And here you can see that metabolic acidosis, the change in the pH is going down, right? And the H plus is going up. We know that when the H plus goes up, pH goes down. What is the primary disturbance? The primary disturbance is in the bicarbonate, because it's a metabolic problem and the bicarbonate goes down. If you remember from it, if you bring it down, the pH will go down, right? And here you see a secondary response. We're going to describe it later. What is the secondary response? Just right now focus on the primary disturbance. The metabolic alkalosis, the pH goes high and H plus goes down. And why the pH goes high? Okay, just put the arrow here rather than down arrow. And by the way, you just mess it up and you put the arrow like this, and you also mess it up, the pH will go high, right? So then you say the bicarbonate goes high, the pH goes high, and it's a metabolic alkalosis. And this thing you can figure it out by yourself, the respiratory acidosis when the PCO2 goes high, respiratory alkalosis when the PCO2 goes down. By the way, what I skipped, that what is the secondary response? The secondary response thing is sometimes, not sometimes, is called compensation. It's the compensation. It's our body, right? Our body needs to be in a milieu interior, or you can say homeostasis. So it doesn't want to be in an imbalanced acid-base state, right? So when there is a change in the pH, the body try to compensate it. Right here you can see that the primary disturbance is decrease in the bicarbonate. Okay, and the secondary response, you can see that the body tries to get rid of our carbon dioxide. So what it is trying to do? When the bicarbonate goes down, we call it metabolic acidosis. And what the body is trying to do with the respiratory mechanism, or you can say by the lung, because we do our respiration by the lung, right? It is getting rid of the carbon dioxide. So when you bringing out carbon dioxide from your body, what you are causing? You are creating a alkalotic state, right? So this thing is compensating your acidotic state. So again, when you are causing the acidosis, or somehow there is acidosis due to decrease in bicarbonate, you are bringing down the carbon dioxide level also to compensate your acidotic state by a respiratory compensation, and that is bringing down your carbon dioxide. And you may ask how you can bring down your carbon dioxide. Well, you can do it right now. Just breathe in and breathe out and do it faster. I mean, do the whole thing faster, like full breath in and full breath out, full breath in and full breath out, and that thing can lead to a decrease in carbon dioxide. Why I told you to do it, do the whole thing faster? Because if you just do what is this? You are just doing a shallow rapid breathing. The oxygen you are taking may not reach up to your alveoli, and if it doesn't reach your alveoli, the gas exchange will not occur. But when you take the deep breath in and take the deep breath out and do it faster, there will be, this thing is called hyperventilation. So the body tries to do hyperventilation and it gets rid of get rid of the carbon dioxide and to make a compensation. When the bicarbonate goes high, what the body does, it tries to hold the carbon dioxide, or you stop breathing. Suppose you have a metabolic alkalosis and you try to stop breathing because you want to bring more carbon dioxide in, or keep more carbon dioxide in your body, and it is a compensatory mechanism, because when the carbon dioxide goes high, it will produce a respiratory acidosis. So for metabolic alkalosis, you are compensating it by a respiratory mechanism, or simply the opposite, the respiratory acidosis. So again, for metabolic acidosis, you are causing respiratory alkalosis. For metabolic alkalosis, you are causing respiratory acidosis. Now, when there is respiratory acidosis, what is happening? You are getting rid, in your body, the carbon dioxide is going high. And as you can see, the bicarbonate level goes high in the body. But this thing is a metabolic procedure. The breathing in function, or keeping the carbon dioxide inside you, is much more easier than this function, because it's a metabolic function. Your cell needs to do this thing after a period, like this bicarbonate retention or increase in bicarbonate, it takes some time. So this secondary response, or you can say when the primary disorder is respiratory, like respiratory acidosis or alkalosis, this secondary response takes time. This thing takes time, or sometimes we say these are the delayed response, because to retain bicarbonate or get rid of the bicarbonate, the kidney needs to work harder. We're going to describe that how the kidney works like this, but this thing takes time. So here we're going to describe some causes and some rules of compensation for the acid-base disorders, and if there is some when we disobey, or when the body disobeys the rules of compensation, we suspect some mixed acid-base disorder. By the way, one thing I want to tell you, that compensation, do you think this compensation is fully done? I mean, if the pH, suppose the pH is went down to 7.3, right? Below 7.35, what you say? It's an acidosis, right? So when the pH is 7.3, suppose it may be a metabolic acidosis. The cause is a metabolic acidosis. That means there is loss of bicarbonate that leads to this condition. And there will be a compensation. The respiratory mechanism or the lung mechanism will try to get rid of the carbon dioxide and bring the pH higher. Do you think this 7.35 will go to the 7.35 to 7.45 level by the compensation? Very rarely. This compensation is not up to the normal. That means that if there is problem with the pH of the blood, if it goes down or if it goes high, whatever, the compensatory mechanism cannot fully bring it back to normal. Cannot fully bring it back to normal. So if you may ask me, okay, so sometimes I see that in the clinical findings that, okay, maybe there is some problem they're discussing, and I can guess that because they will give you this different clinical findings, like they will give you this different levels. I'm talking about exams, of course, and they ask you that what is going on here, and you may sometimes find that the pH level is perfectly fine, suppose 7.39, but when you look at the level of the bicarbonate or when you look at the level of the carbon dioxide, they are not normal, right? So what do you think then? In this case, this is not really a compensation, because what I told you earlier, that when you think about a compensation, it is not bringing the acid base level totally normal limit. But when you see a totally normal acid base, totally normal pH, but still you see there is problem with these levels, bicarbonate or carbon dioxide, you always think about mixed acid base disorder. Mixed acid base disorder. Only that thing can bring the pH normal, but still it's a mixed acid base disorder. Maybe there is a metabolic acidosis, at the same time respiratory alkalosis happening, and these two is you can say wipe off their effect and the pH becomes normal. But in ion you can, when you measure the ions, there will be the disturbances. So again, the compensation doesn't bring the pH to normal. It brings it towards the normal, but not up to normal. But if you find a normal pH and if you find some change in the carbon dioxide or you can say bicarbonate, you think about mixed acid base disorder. Now, some causes of the respiratory acidosis. So I was trying to mark it with my eraser, and you cannot mark it with the eraser. Okay, so respiratory acidosis, there is increase in carbon dioxide level. That's simple. And this causes like heroin intoxication. I put it in the first. Why? Because I love heroin. I mean, not the drug. I mean the heroines. I mean the actresses. I love. Don't tell anyone else. Okay. So this heroin intoxication brings the carbon dioxide in our body, or it causes a depression in our respiratory center, and the carbon dioxide, we cannot get rid of them, and carbon dioxide accumulates and causes respiratory acidosis. Acute lung disease, chronic lung disease, you can get COPD, opioid sedatives, and weakening of the respiratory muscle. This thing leads to a increase in carbon dioxide accumulation in our body, and that leads to respiratory acidosis. Now, I discussed earlier, when you have acidosis in the body, there will be a compensation. The body try to compensate it. But what is the rule of compensation, or you can just ignore this S. What is the rule of compensation? For this metabolic acidosis, Mr. Winters, he gave a formula. I'm not sure if his name is Winters or Winter, whatever. Winter's formula is, it describes it that for every change, for a change in the, you can say, you predict a compensation. You predict a compensation. That means when there is respiratory, I'm not sure. Okay, so no, sorry, I'm sorry. This is not Winter's formula. This is a compensatory rule, Mr. Not the Winter. I'm not sure if Mr. Winter gave this compensatory rule, but the rule is when there is respiratory acidosis, or you are sure that there is respiratory acidosis, there will be a compensatory mechanism, and the compensatory mechanism will be by increasing serum bicarbonate level. But which rule it will follow? This serum bicarbonate will increase by 1 milliequivalent per liter for every 10 millimeter, for every 10 millimeter mercury rise in arterial carbon dioxide. So it means that you are bringing the carbon dioxide up here, right? In the respiratory acidosis, or the pathology is bringing the carbon dioxide up here. So when the carbon dioxide goes up, the compensation would be based on the carbon dioxide. For every 10 millimeter rise in carbon dioxide, there will be increase in serum bicarbonate by 1 milliequivalent per liter. That is the rule of compensation. So why I told you the rule of compensation? If you find other than something, I mean, if there is some deviation from this rule, what do you suspect? You suspect that it is not a compensation, it's a mixed acid-base disorder. So whenever they give you a scenario like there is a pH and you suspect it, okay, it's acidosis, and you see the carbon dioxide and you are very sure that it's respiratory acidosis because carbon dioxide is super high, and then you see it, you see a level of bicarbonate, what do you need to do first? That you need to apply this rule. If you need to see that if there is change, the bicarbonate is changing according to the rule. If it is not following the rule, then you suspect it's not a compensation. There may be a mixed disease going on here, mixed whatever, acidosis, alkalosis, or maybe tubal acidosis is going on here. Depends on the situation. Now, before going to the metabolic alkalosis, I want to discuss this thing, the anion gap, and this is our favorite. We love it, right? What is the anion gap? Anion gap is the difference between measured anion and the measured cation. Okay, so this thing is very important. Measured anion and measured cation. You know what? We are very limited. We are very limited. We have a limitation, and we need to know our limitation, right? And this is our limitation. We cannot measure all the cation and cannot measure all the anion of our body. So you may ask, what is the anions? Anions are the negative ions. Like I can say, bicarbonate is a negative ion. Chloride is a negative ion. Lots of plasma proteins are negative ion. By the way, this is proteins. If you are not understanding my writing, this is proteins. Trust me. These are the negative ions, right? But what you do when you measure it, when you try to measure it, you can measure the bicarbonate level in the extracellular fluid. In the chloride, you can measure it easily, but the protein levels you cannot really measure. Because how you can measure it? Because you cannot bring all the protein out of the body, and there will be a mass, right? Seriously, serious mass. So that's why you cannot measure it. So when you cannot measure it, you depend on what you can measure, right? That means whatever you get, you should be content with it. In the cation, you can see that sodium is cation, potassium is cation, calcium is cation, right? A lot of things are cations. Now, this thing, okay, now there is a difference between this measured anion and measured cation. But the thing is, you should remember that in our body we have a neutral condition, neutrality or neutral condition. We don't have increased cation, or we don't have increased anion unless we have pathology. Unless we have pathology, we have a every cation is equal to every anion. There is no difference. There is no difference in in our total body cation and total body anion. I mean the charge. There is no difference in the charge. Our body is in neutral condition. There is the same amount of positive ions and there is same amount of negative ion. Even in pathology, even in pathology, if there is change in the ions, there will be a compensatory mechanism. The body don't want to go into an acid in more, you can say, polar, or you can say charged state, right? That's why we say that our body is neutral. Now, so when you measure it, when we measure it like this. Suppose we can measure the sodium, we can measure the potassium, and then we can measure the bicarbonate, and we can measure the chloride ion. And if you calculated the amount of them in the extracellular fluid, you'll see there's a gap. That means there are more cations than these measured anions. More measured cation than more measured anion. And this difference is 8 to 16 milliequivalent per liter. Okay, so you may ask why there is this gap, because I just told you that there this in our body the total cations are exactly same in amount as total anions. But why this gap? Because we cannot measure all the anions, right? There may be some anions we cannot measure, like there are some proteins and something we cannot measure. But what we can measure, we can see that there's the difference, and this difference we assume it is due to the anions. The anions we cannot measure. Okay, this gap, this is the gap in our scale, or you can say in our limitation. We have a gap, not limitation. In our scale, we have a gap, and this gap is anion gap. We cannot measure it, right? So this is the unmeasured anion. Okay. So why I discussed it, this anion gap, before going to the metabolic acidosis? Because sometimes you see in the metabolic acidosis they say that there is a anion gap increased metabolic acidosis, and sometimes they say that there is a normal anion gap metabolic acidosis. So let's just discuss the causes first. What are the causes of increased anion gap metabolic acidosis? Here you can say methanol, here you can say uremia, that means urea goes high in the body. Methanol, and that means counterpart of alcohol goes up. Diabetic ketoacidosis, very famous. The keto acids goes high in the body. Propylene glycol, I don't know what is that, but it goes high in the body. Iron tablets or isoniazide causes acid formation by different reactions. Lactic acidosis increases acid level. Ethylene glycol converts into acid products. Salicylate, very important. You see, in the late salicylic poisoning, there is metabolic acidosis. We're going to discuss at the very end about this thing. Trust me, up to that. So you have increased anion gap metabolic acidosis. But why increased anion gap metabolic acidosis? What does it really mean? It means that when you have these products, or when you have increased amount of these products, it may be you are ingesting some methanol, or if there is diabetic type 1 diabetes, more precisely, because type 2 can also have diabetic ketoacidosis, but more perfectly type 1 diabetic people is that they're more prone to having diabetic ketoacidosis. I hope you know what is this, right? There is ketoacid production due to there is lack of insulin. The insulin's control mechanism is lost, and the body cannot control the lipolysis. The body cannot control the gluconeogenesis, and everything is haphazard. Glucose cannot enter the fat cell, it cannot enter the skeletal muscle, and the body thinks there is no glucose, although there is a lot of glucose, and there is production of ketone bodies by the breakdown of the fat. You know it. Now, this diabetic ketoacidosis, or this other cause, whatever it is, there is some acid production in the body. And when there is acid production, if you add it, either you add it or there is acid production, this acid means what? There is increased H plus. There is increased H plus. And what does H plus do? They love something. They love to bind with your bicarbonate. They love to bind with your bicarbonate. Now if you measure it, like the anion gap that we measured earlier, then you see that sodium plus potassium, sometimes we ignore the potassium, and then here is bicarbonate and here is the chloride. And as these bicarbonates are binding with H plus, and they're living happily ever after, because this H plus is now taking away the bicarbonate, you can say the bicarbonate level goes down. the bicarbonate level goes down, and as you can see here, now only chloride is here, now these two guys here, and their gap is increased. And I can give you a silly measurement idea. Like here is 5 sodium, here is 3 potassium, and previously there was, you can say, 4 bicarbonate and 3 chloride. So there's a gap, right? 5 plus 3 equals 8, and 4 plus 3 equals 7. There is a gap of 1. But when H plus came and it takes away all the bicarbonate, this 4 could become 2. Now this gap increased from 1 to 3. So this gap is increased. Although this, you know it, that this is not a calculation, because that's the normal, that's not the normal value of this ions. You know the normal value of ions better than me, and that's why I just give you an idea that how it happens. So that's why you see a increase in anion gap here. Okay, you'll be more clear when we discuss why there is normal anion gap in these causes of acidosis, metabolic acidosis. Here you can see hyperalimentation. Hyperalimentation, what happens here? The person who cannot take food with mouth or normal route, and there you give the person infusion, and maybe on that infusion, maybe this thing doesn't happen right now or in this modern era. It happened earlier, and what happened on those infusion products, there was a lot of proteins, and those protein compounds reacting with your body, metabolizing, they produce some H plus, and when there is increased H plus, there is acidosis. Saline infusion, when you increase saline, there is sodium, and this sodium is all over the body. It goes to the kidney, and the kidney sense it. The kidney see that, okay, sodium is there, there is good amount of sodium, right? And this saline infusion, how it works, I'm not sure. I think it's causing the I'm not sure how this thing happened, but saline infusion leads to normal anion gap acidosis. Look, I'm not sure about everything. Addison's disease, what happens here? There is a decrease in the aldosterone, and when the aldosterone is decreased, there is increase in H plus, because you know that what the aldosterone does. Aldosterone causes the secretion of potassium and H plus, and reabsorption of sodium and water. But now if there is less aldosterone, this thing cannot be happened, and the sodium and the H plus goes high in the body, because the body cannot get rid of the H plus, and there is anion gap acidosis, normal anion gap acidosis. Renal tubular acidosis, another nasty thing. There's several types of renal tubular acidosis. Not into my, I cannot explain that right now because it's the separate thing. Diarrhea, there is loss of bicarbonate, because you know when in our small gut a lot of pancreatic bicarbonate mixes up in the small gut, and when it passes down with diarrhea, we lose bicarbonate, and when we lose bicarbonate, we call it anion gap acidosis. Acetazolamide, it also leads to increased excretion of bicarbonate, because acetazolamide, it blocks the carbonic anhydrase enzyme, and this carbonic anhydrase enzyme, if it is not working, there will be less bicarbonate production. That is another story. If you're going to the kidney physiology, you know it, how it happens. Spironolactone, it blocks the aldosterone directly, and it's almost like the Addison's disease. I'm not sure about the saline infusion, but somehow it also causes anion gap, normal anion gap acidosis. But why normal anion gap? That's the thing. Take this example, diarrhea. I think this is your favorite, right? When this diarrhea happens, there is loss of bicarbonate. When this diarrhea happens, there is loss of bicarbonate, and you can guess that here is the sodium and here is the potassium, and this gap we calculated, here is the bicarbonate and here is the chloride. So this bicarbonate is going down. But you may ask me, okay, when the bicarbonate goes down, the gap should increase, right? Now there is less bicarbonate, the gap should increase, but it is not. Why? Remember what I told you? Our body wants to be in milieu interior, or what is that? Milieu interior means homeostasis, right? Body wants to be in homeostasis. So when the bicarbonate goes down, this chloride works as a buffer and it goes up. Not as a buffer, you can say it's a homeostatic mechanism. The chloride goes up, and I don't know how it goes up. Maybe the body produces chloride more or reabsorbs chloride more, and this gap is not increased. The gap is same because you are losing bicarbonate at the same time you are increasing the chloride level. So this gap remains same, and that's why there is normal anion gap metabolic acidosis. Also, it is called hyperchloremic metabolic acidosis. Now, go back to the previous thing. You may ask me, okay, so why not chloride increasing here in this increased anion gap metabolic acidosis? Okay, so here you see that sodium, potassium, and here you see the bicarbonate, and here you see the chloride, right? When there is the same thing, right? Suppose here is lactic acidosis. When there is lactic acidosis, there is a lot of H plus, and this H plus is coming and binding with the HCO3. HCO3 goes down. You may ask me why the chloride doesn't go higher here. Remember what is happening here? You are adding acid product in this cause of metabolic acidosis. Either you are ingesting some acid or either your body is producing some acid. And that acid, if it is the acid thing, okay, this thing is giving off the H plus, and that H plus is binding to the bicarbonate. But this thing, the other part of the acid, it's an anion. It's an anion. And this thing is sitting here. Now, that's why the body still lives in a neutral condition. Again, when there is increased anion gap metabolic acidosis, what happens here that there is H plus donation from the new acid. Maybe it's a keto acid, maybe it's a lactic acid or whatever. This is donating this H plus. This H plus is binding to the bicarbonate, but at the same time there is this anion of that anion part of that acid, and this anion part is sitting here. And if you calculate this anion gap, now you are calculating the anion gap. By the way, you are not calculating the acid. What you are calculating? We are calculating sodium, potassium, bicarbonate, and chloride. On our calculation, bicarbonate is down and this gap is high, right? In our calculation, in measured calculation, and that's why we get a increased anion gap metabolic acidosis. But in the body there is neutrality because anion is good. Anion is good, and as the and that's why the chloride level don't go higher. But in the normal anion gap metabolic acidosis, when we calculate it, we see that there is increase in chloride and there is a normal anion gap. Again, as there is loss of bicarbonate, but there is no addition of any new acid, right? That's why the chloride should go high. And when the chloride go high and we measure it, and that means we measure the difference, we find a normal anion gap because there is hyperchloremia. But in the previous thing, the bicarbonate goes down, but at the same time you are adding some new anions. And when you are adding some new anions, the chloride need not to go high. And when you measure the difference, you find the chloride level is the same and sodium and potassium their level is the same, but your bicarbonate level goes down and the gap goes higher. And that's why this is the difference between increased anion gap metabolic acidosis and normal anion gap acidosis. And pardon me, I couldn't describe why this thing happens. I'm a mediocre student. So here's the thing, that rule of compensation, how you compensate this thing. This thing is important because that time I confuse it with the Winter's formula, and here's the Winter formula works. What happens? It's a predicted compensation. Same thing. You predict a compensation and you look at your original compensation, and if there is change from the rule, you suspect something else. Because what I told you earlier, that never it's gonna be normal just by the compensation. Or in other words, the compensation cannot bring your acid-base status to normal. It can bring towards normal, but not fully normal. And here's the Winter's formula for metabolic acidosis, that we know that when the metabolic acidosis happens, the bicarbonate goes down, right? And I'm using this more romantic color. Blue is the romantic color, right? So what is happening, that when there is metabolic acidosis, the bicarbonate goes down and there will be a decrease in there will be a decrease or increase in well, there will be a decrease in carbon dioxide level, because when the carbon dioxide also goes down, there will be a respiratory alkalosis condition, and that will try to compensate your metabolic acidosis condition. And what is the rule it follows? How you measure it? The compensation rule is arteriolar PCO2 should be 1.5 times serum bicarbonate plus 8 plus minus 2. This thing varies from different books. I just took it out of something and I paste it here. Don't take it as accurate. So this is the rule of compensation. The arterial PCO2 will be changed like this. It will follow this compensatory rule, like 1.5 with your measured bicarbonate and plus 8 plus minus 2. If it breaks the rule, then you suspect there may be some mixed acid-base condition is going on. Okay, so whenever, usually in your exam in USMLE step 1, you may find this one only. The Winter's formula is most commonly tested, because the other thing is more vague, and those are more complicated to calculate. So this thing is usually more frequently tested, that they test you if you know the Winter's formula. So at least if you forget about the other compensation, at least try to memorize this thing, how the Winter's formula work. Again, you first you look at the bicarbonate level, and then you calculate your predictive arterial PCO2 level, and then you look at your actual clinical PCO2 level. And if you see that the PCO2 level is not matching with your predictive or calculated PCO2 level, there will be some mixed condition going on. Now, the other things are much more easier, like causes of respiratory alkalosis. There is hysteria, you are breathing out everything. Hypoxemia, there is less oxygen. Maybe you are in the top of the hill. Maybe you went to play in the Bolivia, where Argentina loses every time. And salicylates, in the early salicylate poisoning, there may be respiratory alkalosis. As I told you earlier, that we're going to describe the salicylate at the very end. Pulmonary embolism, what happens here? It's another story, it's a big story, I'm not going over it. There is VQ mismatch, and there is hyperventilation, and carbon dioxide goes out more readily than you take in oxygen. As there is VQ mismatch, there is dead space formation, and you cannot take the full oxygen in. What is the rule of compensation? Again, you don't need to really memorize it, but if you know it, that's very good. Respiratory alkalosis, there will be increase. When there is respiratory alkalosis, you can guess that there is a decrease in PCO2. So the compensation will be an increase in serum bicarbonate, and by 1 milliequivalent per liter. Okay, I'm sorry. There will be a decrease in serum bicarbonate. Look, I'm confusing it. So when there is decrease in PCO2, you want to decrease the bicarbonate also to bring in a opposite change. Like here is a respiratory alkalosis, you want to do a metabolic acidosis and try to compensate it. So there will be a decrease in bicarbonate, serum bicarbonate, by 2 milliequivalent per liter for every 10 millimeter of mercury decrease in arteriolar PCO2. Okay, so this is the rule of compensation. And again, if you break the rule, there may be a mixed disease. Now, here's the cause of metabolic alkalosis. It can be loop diuretics, it can be vomiting, it can be hyperaldosteronism, it can be antacid use. So now, the rule of compensation. Before going to the cause again, the rule of compensation, when you have metabolic alkalosis, there is increase in HCO3, right? There is increase in HCO3, and the compensation should be a increase in PCO2, increase in arterial PCO2. By the way, this thing is very harder, because the people will try to stop breathing. How you can increase the PCO2? You just sit there and you stop breathing, and there will be accumulation of the PCO2. But how long you can do it? there will be a hypoxic drive. When you try to accumulate the carbon dioxide inside you, there will be a hypoxic drive, and your medullary center will poke you why you are not breathing, and then you start breathing again. So this thing is hard to gain. But if there's the compensation, it is like the arterial PCO2 will increase by 0.7 millimeter of mercury for every 1 milliequivalent per liter rise in serum bicarbonate. Okay, so this thing is the rule of compensation for metabolic alkalosis. Now, what you need to do that why this metabolic alkalosis happens. Suppose in the vomiting, take into example the vomiting. What happens in vomiting? You are losing the HCl. You are losing the HCl, and that's why you see that when you are losing the HCl, specifically the H plus you are losing, there will be a lot of free bicarbonate in the body, right? So when the bicarbonate increases, we call it alkalosis, and this is due to some metabolic condition because you are getting rid of your H plus and bicarbonate increases. You call it metabolic alkalosis. Okay, and also in the thiazide or loop diuretics, there is metabolic alkalosis. Why? In diuretics, what happens? You are getting rid of the water. And sodium and water pass by through the urine, and there is a compensatory mechanism. Remember, what is the compensatory mechanism? That starts on the renin, angiotensin, aldosterone system, and that leads to work of the aldosterone. And what the aldosterone does, it excrete H plus and potassium in exchange of sodium and water. So now if you get rid of the H plus from the body, again your body is having an alkalotic condition, right? Or the mineralocorticoid excess, like aldosterone excess, you can guess that it can lead to metabolic alkalosis. Now the thing is, one thing I didn't discuss is that in case of acidosis, the kidney tries to create ammonia. The kidney try to produce ammonia. Why it try to produce ammonia? In case you know that the kidney cells, they have through the blood the glutamine, the amino acid comes inside the kidney cell. This is a very small kidney cell. Let's make it larger. So this glutamine comes inside the kidney cell, and this glutamine converts into glutamate, and this glutamate, when it converts, there is release of ammonia, and this ammonia goes into the tubular lumen, and this is the blood side, right? Now this glutamate eventually converts into, I think it gives rise to carbon dioxide, because this thing is amino acid metabolism. It gives rise to carbon dioxide, and this also H plus, it gives rise to H plus, and also in your blood, when there is acidosis, there will be H plus, and together this all H plus comes to the tubular fluid, and this NH3 binds with those H plus and converts into NH4 plus, and they get rid, or they pass through the urine and go out of your body. So this is what? This is the renal ammoniagenesis, or renal buffer system, renal intrinsic buffer system in case of acidosis. This thing is other than the, you can say, the respiratory compensation. And also you may want to know that this carbon dioxide, what happens to this carbon dioxide? It can convert into bicarbonate. And this bicarbonate goes inside the blood. Okay, and it try to replenish the bicarbonate store. So this kind of thing happens, like renal ammoniagenesis happens in metabolic acidosis. Okay, all right, so what I told you at the very end, we're gonna describe it, the salicylic poisoning. Then I will stop my this boring discussions. I think you are I hope you are not slept yet. I mean, by listening to me, you may have a very high, you can say, tendency to go to sleep. Okay, so now what happens in salicylate intoxication? Salicylate intoxication. So here, what happens acutely there will be respiratory alkalosis. Respiratory alkalosis. Because this salicylate, when they accumulate acutely, they go to the respiratory center and they stimulate the medullary respiratory center, and there will be a respiratory drive. That means there will be increased ventilation, and this increased ventilation leads to decrease in carbon dioxide level, and that leads to respiratory alkalosis, right? But when this salicylate accumulates in the body, what is the other name of salicylate? Salicylic acid. So you're seeing that it's the acid content. It is acid content. So when this thing accumulates in the body, it will work like a new acid product. And I hope you remember, when a new acid product is added in the body, that leads to a anion gap, increased anion gap metabolic acidosis. It will lead to increased anion gap metabolic acidosis. Also, this salicylic acid, other than its own acidotic function, what it does, it increases the lipolysis. When it increases the lipolysis, there will be ketoacid production from the fat breakdown, and that is another acid product. Also, this salicylate, they uncouple the very famous, this is not the correct spelling, I hope you know what is the correct spelling of couple. They uncouple the oxidative phosphorylation, and when they uncouple the oxidative phosphorylation, I hope you know this oxidative phosphorylation happens in the inner mitochondrial membrane to produce the energy, right? Where the TCA cycle runs, at the same time there is transfer of the FeDH2 and ADH2, and they transport the electron as a high energy molecule. And at the very end of this transport mechanism, there is a very famous reaction going on. The ADP converts into ATP with the help of ATP synthase, and a proton gradient is needed there, right? So there is two reaction actually happening in this electron transport mechanism, or oxidative phosphorylation. One is the oxidation, another is the phosphorylation. Oxidation is this transport of electron. That thing is oxidation, because we know that some very famous reaction, redox reaction, it involves oxygen receiving or delivering. And as there is oxygen transport in this electron transport chain, there is oxidation reaction, and at the very end, when the ADP binds with the phosphate, we call it phosphorylation. Now, when this thing is uncoupled, that means oxidation is going on by itself and there is no phosphorylation, there is no connection between oxidation and phosphorylation. It can happen due to different causes, I'm not going over them. Then there will be less oxygen production, or you can say less ATP production. Simply, there is less ATP production, and when you have less ATP production, there will be a lot of disturbances in your metabolic cycle. There will be a lot of disturbance in your metabolic cycle, and there will be a very sad thing that will happen, that body will try, when the body understands that oxygen is of no use, the body shifts its energy production into anaerobic cycle, and anaerobic cycle usually gives rise to lactic acidosis, and that is another acid. So lactic acid, here is ketoacid, and here salicylic acid. All three of them, they are acidic component, and eventually in the chronic salicylate poisoning, they build up in the body and causes metabolic acidosis, and that is increased anion gap metabolic acidosis. Okay, so I'll stop now, and thank you very much if you listened up to this. I'm not sure if you did, and okay, take care. Goodbye.